Yeah, Dr. Aissa Bouaissi hold a master in chemical engineering and PhD in civil engineering materials from the University of Plymouth, UK. His research interests cover the field of OPC-free cement and concrete and eco-friendly materials, application of chemical and physical processes in industrial waste and byproduct. Previously, he worked as a senior process engineer in national and multinational company in Algeria, where he built his expertise in well cementing service and the oil and gas industry. Dr. Bouaissi is a member of the editorial board of Journal of Knowledge-Based Engineering and Science and a guest reviewer with several journals. Dr. Bouaissi's last publication was a chapter in a book titled Zero Energy Buildings, A New Approaches and Technologies. So, please, you can start your presentation now, but it's not in full screen mode. Your presentation.
Not in full screen?
Yeah.
Oh.
So,
I think we still have the same problem, like.
But maybe you can do with that. It's not full screen, but yeah, you can do with that.
Is it channel?
Yeah, maybe you can do with that with this mode.
Okay, you have seen this one.
Yeah.
Yeah. Okay, thank you, Dr. Bao, for the presentation. So my presentation today is about the research on organic concrete utilizing different material, including fly ash and slags. So the presentation is divided in 3 main sections. So the first one is giving like some statistics and issues about the OPC. Then moving to geopolymer or alkaline activator material, a process and mechanism. And the last part about the research, objective research approach and results. So starting about for the first part is the statistic about OPC is, as you see in this picture, that the production of OPC is keeping growing dramatically in the world. And back onto this statistic in 2017, so the production of the wood is 4.5 billion ton around the world. And that production is mainly divided in 3 main parts in the world, coming in the first place China, followed by India, then the US. So this mass production of OPC provide a lot of problems and issues. And these issues can be described in the conception of natural resources, because it's required like quarries, and also the intensive of consumption of the energy. To produce 1 ton of the OPC, it required like more than 125 liters of fuel and more than 118 kilowatt hour of electricity. And the second main point also is the emission of the CO2 in the atmosphere. So about 8% of the world emission of the CO2 comes from the production of cement and concrete. And this comes like 3 times more than the global aviation. And also the main properties of the product made from the OPC, it gives us like a very poor immobilization of the contaminant when used in a different environment, and also can't stop or can't resist to the harmful chemicals when put in the soil or in the ground. So moving to the second part, which is the geopolymer, or sometimes we call like alkali activated materials. So what is it? It's like a family of the mineral binders. And these geopolymers are mainly common in one properties, which is the crystalline phase or amorphous phase of each of these minerals. So it is very similar to zeolite, because it has like a combination between the silicate and aluminum in a way it's present in amorphous form or microstructures. So for this reason, it's like has like a very similar properties to the zeolite. In a simple way, so what is geopolymer? It's a combination between a raw material, generally the precursors, comes from like byproduct, then activate this raw material using a different solution, chemical solutions, mainly based off alkaline solutions, and then added a filler like aggregate or sand to produce or to obtain your mortar or concrete. So what's the main mechanism in geopolymer or alkali activated materials? It's mainly based on the way how the chemical solution we use react with the binder. So for example, if we use the alkaline solution based on sodium silicate and sodium hydroxide, so that solution will dissociate the material, mainly is like, for example, fly ash or slags, and that dissolution which makes to produce more ions and cations. That ions and cations react together to produce a form of gel. We call like a gelation phase. And that gelation phase with more rearrangement and orientation, so build like a new bonding and new link across to formulate the growth or the polymerization process, then the hardening process. So why byproduct material? So we can see that the main material or byproduct material which maybe exists in the world is the fly ash, another slags like magnesium slag or kaolin clay or other like rice husk or a different one. So why this raw material? Some statistics just present in this table, it shows the massive production of each single raw material or byproduct material in the world, and it comes from the US or different countries like the EU or China. All the numbers here is in a million ton. For example, fly ash in the US, the production is more than 131 million ton yearly. And in the EU, it's more than 125 million ton a year. And the quantity is quite double in China and India alone. The same for KBES, the production is 1 billion ton of iron can be give us or produce 250 million ton of the slags. So if we can see the ratio here between, for example, the slags and the main materials comes from like steel, is like a ratio is like 0.2 to 0.4. So the main problem proposed by this waste material or byproduct material in the past was disposal. So the fly ash, for example, it used to be entered in the flue gases and released at the atmosphere. But a new legislation in the US forced and required the producer to use or to capture that fly ash and recycle it or dispose it in controlled places or areas. However, more than 65% of the fly ash produced in the wood is disposed in the landfill or the lead ponds. Hello.
Yeah. You have some.
Yeah.
Yeah.
Okay. Because I can't hear anyone. Okay. So moving to the third part is about the research project and the results we come out. So the research approach was divided into investigations in nanoscale.
But your slide, we see only your screen.
You see it?
Okay, yeah.
Perfectly. Yeah. So I said the research approach divided into investigations, the nanoscale and the microscale. So for the nanoscale is the characterization and define which kind of material and the final product we use. So we follow the particle distribution analysis PSA, the X-ray diffraction, XRF for the chemical composition, for the bonding is the FTIR, and for also the microstructure microscopy, we use the SEM EDX, and also we use the optical microscopy for the concrete to see the bonding between the aggregate and the paste. On the other hand, so the microscale study focused on the hardened properties, compressive strength, splitting strength, and the fresh properties, certain time workability. Also, we studied durability using a chloride diffusion test and residual strength when the product exposed to high temperature up to 1,000 degrees. And also, we studied the dynamic behavior of the paste. So, a result as shown in this figure is the compressive strength of the Geopolymer paste in a comparison with reference of handled fly ash. So with a different percentage of GGBS and magnesium slag. So it's very clear that the 28 days compressive strength obtained for our paste in the left hand. So it's the highest value when it's loaded with GGBS. Certainly, that one, when converted and loaded with high magnesium slag, the optimal formula we obtained from the GGBS, we loaded with the high magnesium slag. It gives us like a 10% from the high from the magnesium slag, give us the high compressive strength with 60 megapascal in 28 days. And the fresh properties, so we test the slump test and the setting time for both, for paste setting time and slump test for the fresh concrete, as you can see on the pictures. And it has like a very good slump, as you can see here on these figures. So on the setting time, it's quite longer because it tests for the paste, only for paste. And usually the geopolymer has like a very long initial setting time, then a quickly hardening on the final time. And the slump, we use like a repetitive slump to see how it's like keep its slump with time. After 40 minutes, so we did like different slumps and see what's happened for the slumps. So the initial slump was like 22 centimeter. It was like a very workable concrete and with very good flowability. And then that slump is just reduced with time, but it keeps its workability until like almost 4 hours. So this pictures just show the regulation we follow to test the compressive strength. It's a cubic of 10 centimeters, 15 centimeters, following the STM standards. And also here for the splitting, we use the cylinders and we calculate the splitting tensile for the concrete. And the casted samples, as you can see here, is both on cubic and cylinders, and the test carried on. And this one is the result for the compressive strength and splitting strength for the concrete made, based on the main formulation we found for the geopolymer paste previously. So what we found out here, that the compressive strength is increased with time after 28 days. Then there is like a slightly decrease with 8 to 10%. We believe that decreasing in the strength after 90 days, it could be for the continuity of the geopolymer reaction with the alkali activator and the binder. Why? Because the chemical reaction and the dissolving process for the alkali activator of the raw material, it goes faster in the first time, then continues slowly, which called like microreactions. That one, it's produced more free molecule of water in the system or in the main matrix. And that one, of course, will affect the strength with time. The splitting tensile strength on the right side. So because there is like a linear relationship between the compressive strength and splitting strength, so it increased with time and decreased also after the 90 days with very slight decreasing. But both of them that give us like a very good results and compared to the OPC. The other test we carried on is the rapid chloride migration for the durability test. So a disc of 5 centimeter of depth and 100 millimeter or 10 centimeters of diameter. It used to be saturated inside a calcium hydroxide to prevent any migration of other element or other cations or anions through the system after the vacuum process. Then we saturated inside the mechanism or the system, and we left and we ran the test and get the results after 24 hours as the regulation or the standards. So when we get the cylinders, wash up, dry it, then split it axially and split it with the nitrate solution to see the different color because the nitrate, it gives us a reaction with the chloride migrate or the chloride diffuse inside the samples, and we measure the depth following also always the standards, and the measurement we used and included inside the first and the second fixed law to calculate the diffusion coefficient, and the results give us like a very good classification of the concrete, because the standards, it says that there is like an acceptable concrete or acceptable, good, or very good. So for us, the classification, it was in a good, because the coefficient of diffusion was very low. The other investigation was about the residual strength after exposure to very high temperature. So this picture shows the oven we use, each electronic oven, and different samples carried for more than 3 months. And then put inside the oven following this protocol. So we heat the oven until 900 degrees. Then we put the samples inside the oven for 2 hours. Then we cool down just by opening the oven door and leave it inside the room, and then go for the compressive strength test. So the results represents against the other results found for the OPC and other geopolymer concrete, which has a similarity in terms of material used. So as we can see here in our result in the blue lines, so always the material we use, it has like a very good temperature outstanding in the different stages. So it has like more stability compared to the OPC or others. So always, for example, after a 300 degree until like almost 500 degree, so we have like more stable a product, and then decreasing. But the decrease, it has like a slow decrease. It's not like a sharp or dropping quickly. Yeah. So this one, and also the physical appearance of the material after exposure to temperature shows that a cracking appear after 600 degrees. And the case is not for applicable for the OPC or the others, because for the OPC, it starts like from 250 to 180 degrees, it starts like cracks appearing. That one which support and give like a very good temperature resistance. The other main test we carried on is the impact test for the dynamic behavior. So we use Hopkinson bar pressure test. This test is carried in China. So this is the Hopkinson bar test. It divides in two main parts. The first part is the incident part, and the second part is the transmitter part. So both parts are linked or connected with amplifier to give us the analyze the waves, the transmitter wave through the bars. And this is the pictures. So to get that information, so we have here on the right side, we have a gauge or a sensor to capture or to read the results. So to carry on this test, we need a samples about like 35 millimeter diameter and 18 millimeter of thickness. So for our case, we have 3 different diameters, 33, 36, and 37 millimeters. And in each group, we use a different speed or different impact speed, 2, 4, 6 meters per second. So the samples cutted, polished, and measured, and after that, put in test. So before to carry the test, we need to calibrate and the machine or the equipment without any samples, and filtering the wave to see the clearly, as we see here in the right side. The left side is before the wave filtering, and after that, when we filtered, so we can see clearly the wave of the incident side or the reflected wave or the transmitted wave. So based on these informations, we got the main information we need for analyzing the behavior of our paste or our samples. So the main properties or parameters is the dynamic compressive strength for the samples. So we can see here is the stress against the strain of all the groups. And then we did the same applied the same strength and stress we found in other models. We found to see the convergence or to see the difference between the models exist in concrete in general, it's not in the alkali activator or geopolymers, and ours, and see what's the difference. So for us, because now here it's upload all of them in a different groups, in a different stress strain rates. So we found that there is like a very good approaching between our models in two different strain rates, which limited by 63 centimeter minus 1, and then go for linear increasing. This one explained by the curve of stress strain. So this is example for a group 33 millimeters in a different impact speeds. So at the first stage, we found that there is the curve, it has like a very similar variation patterns in which the stress firstly increased almost linearly here with the strain, and this one is representing the elastic relationship between stress and strain. Then it has like a slow improvement, which is very close here to the linear stage, a slow improvement with the increase of the strain representing this side is the hardening stage. And then finally, in the top here, finally, the stress reached the ultimate value and drop quickly or harshly. And this one represents the compressive failure of the samples. So to see this one in real, so we have the capture pictures, because on each test we have the camera to capture the samples and the impact. So in a different speed, impact speeds. So we found that the samples crashed from like big segments and big fragments to a smaller one and a finer one when the speed increased. And when speed increased, we found that the strength is like has like a sensitive relationship with stress. Yeah, and this one gives us an idea to analyze the energy or the gain energy or absorb the energy by the samples during the impact. So the representation shows is a polynomial presentation fitting. So the energy absorbed is increasing with the strain rate until get or reach the saturation stage where the sample shows the failure or the start cracking. The other investigation is microstructure analysis or investigation. So we took the samples from the paste, we exposed to SEM analysis and study which kind of gel or bonding exists. So we found, as the other presentation shows, always there is the formation of the cash gel or Nash gel, and some of the samples shows the non-reactive or half-reactive of fly ash, which shows in the spherical form, and this is because the time is not going to react, but it has a long time to go because it has a relationship with the quantity of the alkali activator or the ratio of alkali activator you used. So the process here or the reaction is go slowly. So to make sure that the different element exists in the paste are from the raw material and see what's happened for that one. So for the ADX here, it's not clear, but the first image, it shows the presence of the calcium, high calcium, which comes mainly from the KBES. The second one, it represents from the magnesium. And the third one, it comes from the silicate or aluminum, from all of them. The magnesium comes from the high magnesium nickel slag, the third slag we used. So another analysis is the XRD, or diffraction patterns. So we only focus for the third or fourth part on the right bottom here. This is for the product, for the paste. So the main peaks is the crystal peaks appear in the product. And analyzing these peaks, we found that all of them had like the same properties of the raw material it comes from. For example, for the quartz, it's the present quartz in both from fly ash and GGBS. And the calcium, it's mainly count for the calcium divided from calcium carbonate from GGBS. And the magnesium valentine comes from the magnesium of nickel comes from the high magnesium nickel slag. So the fourth part of fourth XRD pattern shows that the three materials have chemically reacted together and the chemical solution as well. So to support these results, we did the FDIR results to see which kind of bonding exists or bonding built during the geopolymer process or mechanism. So it's clearly here that depend on different reference. So we analyze the different bonding found, and our geopolymer we found in green here, it has like a huge hump of the existence of the bonding OH, or sometimes is the water, between the wave number 300, 3,500 and 3,000. And this is explained why the strength is getting dropped after 90 days. So for this quantity of water, because it still exists inside the mechanism, and that one will be evaporate with time, creating microcapillaries, so making the paste or the matrix weaker with time. Coming to the conclusion, so we see that the future trend of geopolymers research shall focus on the understanding of the polymerization mechanism, and this would be a standardized geopolymer for the commercial production. And also, this might include the route of geopolymer synthesis with discernible strength and properties, for example, the material or the stoppable of the activator solutions or other chemical activators maybe we can use. And thank you very much for your attention.
Thank you very much, Aissa. Okay, so because we don't have a